In this video, we will look at the derivation of the kinematics equations for constant acceleration. This talk is fairly equation heavy, so for some of the slides I will not have much to say. I'll simply show you the steps in the derivation. I encourage you to pause the video at those times and work through the in-between steps by yourself to fully understand the derivations. We start with our definitions of velocity and acceleration. Velocity is the rate of change of position with respect to time, and acceleration is the rate of change of velocity with respect to time. So this shows us how, if we are given position as a function of time, we can take its derivative and get velocity. If we are given velocity as a function of time, we can take its derivative and find acceleration. If we want to go the other way, we need to integrate. So first, we rewrite the equations. dx is equal to v dt, dv is equal to a dt, and then we integrate. On this side, we are integrating with respect to x. We can see that because it's dx, and so the limits are values of x, x0 and x1. On this side, we are integrating with respect to t. We can see that because of the dt. So we are integrating velocity, which is a function of time, with respect to time. Since we're integrating with respect to time, the limits of our integrals are times, t0 and t1. Similarly on this side, here we are integrating dv, so we are integrating with respect to velocity, and so our limits are velocities. And here we are integrating with respect to time, and so our limits are times. These equations, this which shows you how to go from position to velocity, this which shows you how to go from velocity to acceleration, this which shows you how to go from velocity to position, and this which allows you to go from acceleration to velocity, these four equations are always true, no matter if the acceleration is constant or not constant. But now let us specialize to the case of constant acceleration. So again, we start with a is equal to dv over dt, rearrange to get dv is equal to a dt, and integrate. The integral of dv is simply v, and evaluated at the limits becomes v1 minus v0. What about this side? A is a constant, and so we can pull it outside the integral. So now we simply have integral dt from t0 to t1. The integral of dt is just t, and evaluated at the limits we get a times t1 minus t0 is equal to v1 minus v0. Again, remember, if you need a bit more time to follow any of these steps, simply pause the video and work through it. In order to make this video a bit shorter, I will be going at a decent pace, but always feel free to pause the video, and if there's something you don't understand, feel free to ask me in person or write me an email. Rearranging this equation, we get v1 is equal to v0 plus a times t1 minus t0. If we set our initial time t0 to 0, and if we call the initial velocity v0, then this is our equation. v1 is equal to v0 plus a times t1. Or perhaps it's more familiar in this form. v final equals v initial plus at. So we have an expression for velocity as a function of time if the acceleration is constant. Again, remember, this equation only holds if the acceleration is constant. If the acceleration is a non-constant function of time, then this will not hold. What about position? We start with this relation. And since we are looking at the case of constant velocity, we can plug in this expression. So instead of v of t, we plug in this. We have that here. v0 is a constant, so the integral of v0 dt is just v0 times t. The integral of a times t, we're just expanding this out. So the integral of at dt is 1/2 at squared. And a and t0 are both constants. And so the integral of minus a t0 is minus a t0t. And then we evaluate at the limits t1 and t0. We get this expression. And once again, we can set t0 equals 0. We can call the initial position x0, the initial velocity v0, and we achieve this familiar form for the final position as a function of time, given the initial position, the initial velocity, the time, and the acceleration. Once again, remember the acceleration is a constant. So, to summarize, we have, for the case of constant acceleration, the following equations, giving us the velocity as a function of time and the position as a function of time. Graphically, what does motion under constant acceleration look like? Well, if the acceleration is constant, then we have a flat horizontal line. In this case, I have shown a constant negative acceleration, but it could be a constant positive acceleration or even zero acceleration. The velocity will be a line of constant slope, and the slope will correspond to the acceleration. We can see that the slope of a v versus t graph will have units of meters per second over seconds, which is meters per second squared, the units of acceleration. This is why the slope of a v versus t graph gives us the acceleration with the appropriate units. In this case, the acceleration is negative, and so the velocity line has a constant negative slope. Integrating once more, we get the position, which is now a quadratic function. Notice how, as we integrated, we went from a constant to a linear function to a quadratic function, a parabola in this case. And for the case of negative acceleration, the parabola is like this. For positive acceleration, it would be like this. How can we interpret and remember these constant acceleration formulas? We can rewrite the velocity equation as v final minus v initial, which is delta v, the change in velocity, is equal to at. If I were to graph an acceleration versus time graph, for the case of a constant acceleration between time 0 and time 5 seconds, it would look like this, a constant acceleration which drops to 0 after that. Notice that the acceleration has value a, and the length of time for which there's an acceleration is t, here in blue, a and t, and this green area is the area of the rectangle. Since it has a height of a and a base of t, the area would be a times t. But we know that the change in v, that is delta v, is the area under the a versus t curve. Remember, v final minus v initial is equal to integral a dt, but the integral only refers to the area under the curve. In this case, the area under the curve is a times t, and so we get delta v is equal to at. This is the graphical meaning of the velocity equation for the condition of constant acceleration. What about the position equation? This time I plot velocity versus time. I assume that we start with an initial velocity v initial and we have a constant acceleration. And so our velocity versus time graph is a line with a constant slope, the slope being a. This acceleration lasts for a time t. We can look at the area under this curve and split it into two parts, a triangle and a rectangle. The triangle has a base of t and a height of at. The rectangle has a height of vi and a base of t. But we know that the change in x, the displacement, x final minus x initial, delta x, is the area under the v versus t curve. But the area of this rectangle is vi, the height, times the base, t. So this brown area is vit, and the area of this triangle is 1/2 base times height. But that is 1/2 t times at, or 1/2 at squared. And so the total area is v initial times t plus 1/2 at squared. But this is just the constant acceleration equation for position. X final minus x initial is equal to v initial t plus 1/2 at squared. In other words, if you had not been accelerating, you would have covered only this much distance, this brown area. But since you were accelerating, you not only covered that, but you also increased the area by this green amount. And this is the total distance covered, the combination of this green and brown area. Once again, here are the expressions for velocity as a function of time and position as a function of time in the case of constant acceleration. Here we have expressions for v and x in terms of a, v0 and x0, as well as t. We can derive other relations by eliminating one of these variables. For example, supposing we want an equation that doesn't depend on time, at least not explicitly. To do that, we have to eliminate time. And to do that, we need to find, first of all, an expression for time so we can replace it. These are our two equations that we are working with, and we want to get an expression for time from one of the equations so we can plug it into the other. Which one should we use to eliminate t? The answer is the simpler one. This is a simple linear equation in t, whereas this is quadratic. It is much simpler to solve this for t. And so we get t is equal to v1 minus v0 divided by a. So now our first equation has been replaced by this expression, and we have our second equation. We can now take this expression for t and plug it in here. And so x0, v0 times t, t being replaced by this, and then 1/2 at squared, 1/2 a, and t squared being replaced by this. We move x0 over to this side, so we have x1 minus x0, and for these terms, we find a common denominator of 2a. This expression looks very complicated, but we see a number of cancellations. This cancels with this, and there is a partial cancellation here. And so our final result is delta x, that is x1 minus x0, is equal to v1 squared minus v0 squared divided by 2a, which can be rewritten as v final squared is equal to v initial squared plus 2a delta x. In this course, whenever you learn a new idea, it's a good idea to think about how it connects to the other concepts that you have learned. In this case, in Chapter 2, we have learned about position, velocity, and acceleration. How do we connect these concepts?
We know that we can go from velocity to acceleration by taking the derivative, that is, feeding in the velocity to this derivative operation and getting the acceleration. And we can go from acceleration back to velocity by taking the integral of the acceleration to get the change in velocity. Similarly, we can go from position to velocity by taking the derivative with respect to time, and we can go back from velocity to position by integrating velocity with respect to time to get the displacement or the change in position. This is an example of a concept map, connecting the concepts that we have learned so far in Chapter 2. As we proceed further into this course, we will learn more and more concepts. Our concept map will get bigger, and each point will have more connections. It is a good idea after every chapter to try and draw your own concept and see how it links to what you have learned before. As you learn more and more, the tree gets richer, bigger, and more interconnected.
Graphically, we can think of these relations as being the slope of a v versus t graph will give us acceleration. The area under the curve for an a versus t graph will give us the change in velocity. The slope of a position versus time graph will give us velocity, and the area under the curve for a velocity versus time graph will give us the change in position. Let us look at one final question that uses most of these concepts. A motorist passes a school crossing corner doing 15 meters per second in a 10 meter per second zone. A police officer on a motorcycle stopped at the corner, which we take as x equals 0, starts off in pursuit. The officer accelerates from rest, so the initial velocity is 0, at an acceleration of 2.5 meters per second squared until reaching a speed of 20 meters per second. The officer then slows at a constant rate until coming alongside the car, traveling with the same speed as the car. Here are a number of questions. How long does the officer speed up? When switching from speeding up to slowing, how far is the officer from the corner? How far is the officer from the car? How long does it take for the officer to catch up? What is the officer's acceleration when slowing? And then we are also asked to draw some graphs for the two vehicles. Pause this video and take this time to try and solve this problem on your own. I will not solve this entire problem, but I will show you the first few answers. In solving these kinds of questions, it is always a good idea to start by making a table of everything that you know and everything that you don't. The first question concentrates on the officer. For how long does he accelerate? So let us focus on what we know about the officer. We know that the initial position is 0 meters. We know the initial velocity is 0 meters per second. He starts from rest. And we know the acceleration is 2.5 meters per second squared. What else do we know? We know that he accelerates until he reaches a speed of 20 meters per second. And so his final velocity is 20 meters per second. We are asked to find for how long the officer accelerates. In other words, what is the time? We start by writing our constant acceleration equations. And see which one can help us. Since we are looking for a time, this equation cannot help us because it does not contain time. It has to be one of these two. This is definitely the easier equation to use. Let us check if we know everything. We know V final, we know V initial, we know the acceleration, and so yes, we can solve for time. Before plugging in numbers, we take this equation and rearrange it to solve for the quantity we want, which is time. We can now plug in the numbers. We see that V final is 20, V initial is 0, and the acceleration is 2.5. Therefore, this will simplify to 20 divided by 2.5, which gives us a time of 8 seconds. This is the answer to the first question: how long does the officer accelerate? In the second question, we are asked, at the time when the officer switches from speeding up to slowing down, how far is he from the corner? In this case, we are asked to find a position. At this point, it is probably good to update your table, since we have found the time that the first interval takes during which he is accelerating. We should update it. We are now looking for a position. So we should use either this equation or this one. In fact, we could use either one of those. Let's go ahead and try using this equation. In this case, we are already trying to find x final, so we don't need to rearrange the equation. Instead, we'll just go ahead and plug in numbers. Luckily for us, x initial is 0, v initial is 0, and so we only have to evaluate this term, 1/2 at squared. X final is then 1/2 times 2.5 times 8 squared. This evaluates to 80 meters. This is the distance of the officer from the corner at the time he switches from speeding up to slowing down. At this point, how far is he from the car? Well, the position of the corner is 0 meters. The position of the officer is 80 meters. What we need to find is, at t equals 8 seconds, what is the position of the car? Since the car was traveling at a constant speed of 15 meters per second, and 8 seconds have passed, we simply need to use this equation to find the current position of the car at t equals 8 seconds. Luckily for us, since the car is not accelerating, this term will not be there. X initial is 0, and so for the car, we simply have X final car is equal to V initial car times t, which is 15 times 8, and we see that this evaluates to 120 meters. Since the position of the officer is at 80 meters, the distance from the officer to the car is 40 meters. These are the questions that I will answer for now. I encourage you to try the others by yourself, and if you get stuck, feel free to come by and ask me. That's all for this video. I'll see you in the next.